All right, today we're going to look at what's called hidden Markov model. So a hidden Markov model is a belief network. So notice here there's a Markov chain at the top from S1 to S2 to S3 to S4 to S5. And each of these have exactly the same parent. So the only parent of S2 is S1, the only parent of S3 is S1. So this is the same Markov chain that we had before, except now we're going to have an observation for these states. And now we're going to have sort of observation I only depends on state I. So we're going to have this model of now. We have a state, and we can have an observation that depends on the state, and now the state's transition. And so now what typically happens is we make the observations of these O variables, we observe these, and we'd like to predict the state. That's the game that we're going to play here. So while these were the ways of doing natural language, hidden Markov models for the traditional way of doing natural language and speech processing, they're not used so much now for that. However, they're still widely used for systems where this really is time. So when this really is time, this is a very good model. So things like biotic localization, we're going to give an example of, use this. If you have we'll see later on, if you have it's always going to be better just not to believe the observations, but to try to predict where you were from before. So it's always better to try to predict where you were from before, as well as use this observations. So this is just a belief network. So you can just looking at the network, you can tell what probabilities need to be specified here. So in particular, we need the P of S0 specifies the initial conditions. The probability of Si plus 1 given Si specifies the dynamics, so each variable depends on its predecessor. And this gives us the sensor model. The probability of our observation I depends on Si. And that's all we need. We can just read from the belief network what we need to do here. Okay, so the typical problem we're going to look at is what's called filtering. And what we're going to try to do is we're going to try to get the probability of state Si given the history of all observations up to state I. So we're going to observe, given all the states in the observations, we're going to work out what's the probability of this current state. And what we're going to do here is we're going to observe OI, O0, and observe S0. So we're going to use probability of S0 given O0. And that's basically just Bayes' theorem. Then we're going to observe O1 and query S1. So then the probability of S1, you have the probability of S1 given all of its observation history. Observe O2, then query S2, where we've got the whole observation history we're going to condition on. Okay, that's the problem of filtering. It's probably the most common sort of query that we're going to do when we do use a hidden Markov model. There are other things we do, like something called smoothing, which also takes into account some future observations and is used to smooth the past observations. So by having some observations about the future, you can actually make a better prediction of what the state is. But now we're just going to look at the problem of filtering, which is predict the current state based on the history of observations. Okay, so it turns out that the probability of Si given O0 up to OI is proportional to the probability of OI given the state and the history of OI, the previous ones times the probability of the previous states. Now, this is just Bayes' theorem. So all we've done is just swapped Si and OI. So this is exactly Bayes' theorem, where the right-hand side there is just O0 up to OI minus 1. So this is just Bayes' theorem. The proportionality is just what we're going to do is we're going to normalize at the end to create a probability. And this is equal to so this one, the probability of OI given Si is just because OI only depends on Si. It's independent of the previous one. So this is actually one of the values that we're given. And to compute this right-hand one, we're going to we're going to sum out Si minus 1. We're going to sum out the previous state. It's the probability of Si given Si minus 1 times the probability of Si minus 1 given all the previous ones. And so now this is interesting because this is now interesting for a number of reasons, not least because this is given to us as part of the model. This is given to us as part of the model. So both of those two specified as part of the model. And this is just the previous one. So this is just the previous one we've just computed. So we can do this recursively or in a dynamic programming way of once we've computed that, we can transition to the next state, absorb the observations, and then keep going. So that's what's going to happen here. So this is just variable elimination, by the way. So we have the previous state observation, we're going to transition to the next state, then we're going to observe the state, we're going to absorb the observations. Okay, so here's an example of doing this. So this is what we're going to do in class. We're going to look at an example of localization. So what we're going to do is we have the location. We're also going to have actions in here. So we're going to know what actions occurred in here. So it's not that weird. So we're going to know what actions we carried out. And the location at one time depends on the previous location and the action. So this is going to be like our definition of actions before. So the location now depends on the previous location and the action. And now we have observations under here. So the observation only depends on the location in this model. Okay, so that's this example of localization. And the idea is knowing all the actions and knowing the observations, where can we locate the object? So this is the sort of thing that we need to do for self-driving cars. And in fact, this model was the one that was used by all of when they used to publish how they worked, when the people used to publish how their localization for self-driving cars worked, they all look like this. So you all use this, everyone used this model, and there's no reason to think that they don't use this now. They just now have more fancy observation models than they did then. Okay, so here's the example we're going to look at in class. So go doors at position 2, 4, 7, and 11. So there are 16 locations. There are doors at certain positions. There are noisy sensors. So that's all we know. It turns out that we're going to have this loops all the way around this location. There are going to be noisy sensors. So the sensors are either going to detect a door or not a door. And the dynamics is stochastic. It's there's lots of noise in the dynamics. And the robot's going to start at an unknown location. It's going to move left or right. It's going to observe the door, and it's going to locate itself. And this turns out to be really challenging if you think about it, because it's lots of ambiguity. There's going to be lots of noise in here. The noise models we're going to do is, if you're at a door, you can observe the door 80% of the time. Okay? If you're not at the door, you're going to observe the door at 10% of the time. So this means it's going to be a 0.2 chance that you are at the door and you don't observe a door, which is going to be a false negative, right? And this is going to be a false positive. So you're not at the door and you're doing it. So there's a 10% false positive rate here. So there's a fair amount of noise just in the sensor model. So just knowing this, we can't really determine what's happening very well. And here's my dynamics model. So if you're at location, if you're at location L and you go right, then you only succeed 80% of the time. So you only actually end up at the location L plus 1, right? If you're at this location and you end up staying at the location with chance 0.1, you end up going forward 2 steps with this probability, and you end up going to some random place on this network as about 2% of the chance. Okay, so all this arithmetic is modulo 16, and basically the action go left goes the same to the left. So this is quite noisy. And so what we're going to do in class is we're going to look at, someone is going to have the ground truth. So they're going to know where the robot is. They're going to know where the robot is. They're going to tell us what the observations are and what the actions are. And we're going to try and see whether we can locate the robot, find out where it is. And we'll find out that just using variable elimination in the model we saw there is actually very good at this. It's much better than you might think we could do, given all of this noise in dynamics. It only does what we tell it to do 80% of the time. And these are quite noisy sensor models. So it's quite noisy sensor models. And it's not much signal in here, right? Because you're going to find out where you are. The only difference between these things is whether there's a door or not a door. And they're quite spaced out. And there's a There is a pattern here, but you've got to be able to find that pattern. Okay, so that's the challenge. So we're going to do this. We're going to look at that example. And then we can actually look at a problem of sensor fusion. So what we'll do here is we're going to include, so now we've got the same model, there's locations depend on the actions. And now we're going to have two signals here. There's a door signal, which is D0, D1, D2, D3, D4. So we've got that, but we've also got a light signal about can we detect there's light? Because a different part of this will have a different light. And we can combine these signals into giving a location just with this model here, and it's exactly the same model before. We're just going to use variable elimination again. So we know how to implement this, right? We know how to implement this because it's just variable elimination. So when we start building these networks of saying what depends on what, we can write down these quite complicated ones. So because we already have an algorithm to solve this, we can solve it quite well. So we're going to play with this in class.